Look at your thumb. Press it hard against the surface of whatever desk or table is nearest to you. You can feel the resistance. You feel the bone, the physical mass of your own anatomy. You are entirely convinced that you exist in three dimensions. You have width, you have height, you have depth. But you don't. The depth is a projection. Every single thing you are experiencing right now, from the weight of your feet on the floor to the space between your face and this screen, is a phantom. It is a biological rendering of data that lives on a flat, two-dimensional boundary at the absolute edge of the observable universe. You aren't sitting in a room. You are a hologram, a projection of information smeared across a distant horizon. I know, it sounds ridiculous. It sounds like the kind of pseudo-philosophy people throw around when they want to seem deep online. When I first encountered this idea, I dismissed it immediately. I assumed it was a mathematical artifact, some weird quirk in an equation that physicists use to balance their ledgers, but has nothing to do with actual rocks or human bodies. We live in a thick world. We break bones, we spill coffee. Things occupy space. Then I read Leonard Susskind's 1995 paper, The World as a Hologram. I haven't looked at a room the same way since. Susskind wasn't trying to be poetic. He was backed into a corner by a paradox that threatened to destroy the foundation of physics. The problem starts with black holes, but forget the usual sci-fi imagery of giant swirling drains. Think of a black hole as a storage device. If you want to store a collection of books in your house, you need a room with enough volume. If you double the dimensions of that room, your storage capacity multiplies by 8. Volume scales by the power of 3. That is basic, unshakable geometry. But black holes don't play by that rule. They can't. If you drop an object, say a hard drive full of data, into a black hole, that data doesn't get packed into the interior volume. It gets stuck to the outside skin, the surface area. If you double the size of a black hole, its information capacity increases by 4, not 8. It scales like a flat sheet, not a box. Think about how terrifying that actually is. The absolute maximum amount of information you can cram into a region of space is limited by the surface area of the wall surrounding it, completely ignoring the space inside. It is as if the interior of the room doesn't actually exist. The boundary is the only thing that holds reality. Wait, let that sit for a second. If the surface is where the information lives, what happens to the stuff inside? What happens to us? If a black hole forces 3 dimensions to compress into 2, what if the wider universe is doing the exact same thing? What if the horizon of our cosmos is the real hard drive, and we are just the software running in midair? This isn't a metaphor. That is the part that keeps me up. The math suggests that the third dimension, the depth that allows you to walk across a room, is a collective illusion generated by the interaction of data pixels on a distant boundary. We are like characters on a television screen who think they can walk deep into the background, completely unaware that they are flat ink on glass. But if we are just a projection, it means there is a limit to our resolution. If you zoom in close enough on a digital image, the picture breaks. The smooth lines turn into jagged blocks. If our universe is a holographic projection from a distant, flat boundary, then space itself should have a grain. Your hands should have a grain. And people are actually looking for it right now, using machines that can measure distances smaller than an atom. They are looking for the blur at the edge of reality. 10 to the minus 35 meters. Write it out. A decimal point followed by 34 zeros and a lonely one. That is the Planck length. It is the absolute bottom floor of reality, a scale so microscopic that the word small loses its meaning entirely. If you were to blow a single atom up to the size of the entire observable universe, the Planck length on that scale would be roughly the height of an average tree. You cannot have half of a Planck length. Space cannot be divided any further than that. It is the fundamental pixel size of our existence. For decades, physicists assumed these pixels were arranged like bricks in a house, stacking up left to right, forward and back, up and down, to build the three-dimensional space we walk through. It felt obvious. But in 1993, a Dutch physicist named Gerard 't Hooft published a paper titled Dimensional Reduction in Quantum Gravity. He looked at that pixelated floor of reality and saw something deeply wrong. He realized that if you try to count those bricks in three dimensions, the math self-destructs. Imagine a storage warehouse. Under normal rules, if you want to store more boxes, you build a bigger warehouse. You utilize the volume. But 't Hooft discovered that if you try to cram too many data pixels into a three-dimensional region of space, something catastrophic happens. Information carries energy. If you pack too much information into a dense volume, that energy creates a gravitational pull so intense that the space collapses into a black hole. Think about that restriction. It means you cannot have a warehouse full of infinite data. The moment the interior gets too crowded, the universe steps in and slams the panic button. It is like trying to pack a suitcase for a trip. In our everyday experience, if you force too many heavy clothes inside, the seams rip open. But at the quantum level, the universe operates under a completely different set of rules. When you overpack the suitcase, the clothes inside don't burst out. Instead, they flatten. The sweaters, the shoes, the jeans, they suddenly lose their depth and smear themselves across the leather exterior of the bag. The inside of the suitcase becomes completely hollow, a void, while the entire inventory of what you packed is encoded entirely within the texture of the outer zipper. That is what a black hole does. It takes a three-dimensional history and flattens it into a two-dimensional surface. But 't Hooft didn't stop at black holes. He looked around his office. He looked at his desk, his chair, the air in the room. He realized that if the maximum amount of information any space can hold is determined by its surface area, then the third dimension is redundant. It is an illusion. The universe is actively hiding the fact that it is a flat sheet by painting a convincing picture of depth over our eyes. We accept this because we feel the depth. We move through it. We assume that for a shadow to exist, there must be a solid object casting it. But what if the shadow is the only thing we can touch? If 't Hooft was right, the true laws of physics, the fundamental code that dictates how electrons spin and how your heart beats, do not take place in the room with you. They are written on the distant walls. Pointing at the space between your hands right now is meaningless. There is nothing there but a projection. But this leaves us with a devastating question. If our three-dimensional world is just a rendering of flat data, what is doing the rendering? Where is the engine running this simulation? To find it, a young physicist had to reimagine the shape of the entire cosmos, creating a universe that shouldn't exist, just to prove that ours does. 22,000. That is the number of times other scientists have referenced a single paper published in 1997 by a 29-year-old Argentinian physicist named Juan Maldacena. His work, The Large N Limit of Superconformal Field Theories in Supergravity, became the most heavily cited piece of theoretical physics in history because it did something that should have been impossible. It built a mathematical bridge between two completely incompatible realities. Maldacena constructed a toy universe. To visualize it, imagine an ordinary soup can. Inside the can, you have a world that feels familiar. It has three dimensions. Objects move through it, rocks fall, and gravity bends the fabric of space. This is Einstein's playground. But this soup can has a boundary, a flat two-dimensional skin wrapped around the outside. On this outer label, there is no gravity at all. There are only quantum particles, buzzing and colliding like static on a dead television screen. Maldacena proved that everything happening inside the volume of that soup can is perfectly mirrored by the flat behavior on the surface. They are not two separate systems. They are the exact same physics, just written in two different languages. A star collapsing into a black hole inside the can is mathematically identical to a specific swirl of quantum fluid on the label. I spent days trying to find a loophole in this logic. It feels like an intellectual cheat. When you walk across a room, you feel the distance. You feel the time it takes to get to the door. But in Maldasena's universe, that distance is a phantom born from a quantum property called entanglement. If two pixels on the boundary are tightly linked, the object inside looks close. If their connection weakens, the object appears to move far away. Space isn't the stage where the play happens. Space is just the scenery projected by the actors on the wall. But critics immediately pointed out the catch. Maldasena's soup can universe doesn't look like our home. His model is filled with a strange, negative energy that warps the cosmos inward. Our real universe is expanding, blowing outward like a balloon. The math worked beautifully, but it worked in a fictional mirror. To see if this holographic trick applies to the actual dirt under our fingernails, scientists had to stop staring at clean equations. They had to look at the messy, real-world fabric of space itself. They went hunting for the physical noise at the bottom of the world. And what they found hints that the illusion is already breaking. If you aim a high-powered laser pointer at a wall a mile away, you expect the dot to stay perfectly still. It should be a clean, motionless pinprick of light. But if the universe is a holographic projection, that dot will shake. It will tremble with a microscopic jitter, a random twitching caused by the pixels of space itself shifting underneath the beam. In 2008, a physicist named Craig Hogan published a paper called Measurement of Quantum Fluctuations of Spacetime. He didn't just suggest that our reality has a resolution limit. He claimed we could actually hear the machine running. He called this phenomenon holographic noise. It is the existential equivalent of the static you see on an old television when you tune it to an empty channel. Hogan argued that this fuzz isn't coming from malfunctioning equipment. It is the sound of the universe buffering. To find out if he was right, a team at Fermilab spent years building a device called the holometer. Picture two long, reflective tunnels buried in the dirt of Illinois, arranged in a giant L shape. They shot intense lasers down these tubes, bouncing the light off mirrors to see if the beams arrived out of sync. They had to isolate the machine from every possible earthly disturbance. The rumble of distant traffic, the changing of the tides, even the microscopic vibrations of the footsteps of the scientists walking through the parking lot had to be canceled out. They were looking for a vibration smaller than the width of a single atom. Think about a digital movie playing on a giant screen. If you sit in the back row, the image looks solid. A person walks across the frame, and their movement seems perfectly fluid. But if you walk down the aisle and press your nose directly against the glass, the illusion breaks. The person dissolves into a grid of colored squares. Hogan believed the holometer was our way of walking up to the screen and touching the glass. I remember reading the initial updates from that team and feeling a genuine sense of dread. If they found that jitter, it meant everything we see is a rendering. It meant that when you hold a cup of coffee, your fingers aren't touching ceramic. They are interacting with a pixelated field that merely reports the sensation of heat and weight to your brain. The holometer eventually ran its tests. The data came back, and the results were clean. It didn't find the specific noise Hogan predicted. The scientific community breathed a collective sigh of relief, declaring the holographic threat averted. The world was solid after all, but they celebrated too early. The holometer only proved that one specific type of pixelation didn't exist at that exact scale. It didn't kill the hologram. It just meant the screen was much higher resolution than we thought. And while we were looking for the grain of space in a quiet tunnel in Illinois, another group of researchers was looking at the horizon of our universe, realizing that the data defining our lives is running out of storage space. If you split an apple in half, you get two pieces of fruit. If you split a magnet in half, you get two smaller magnets, each with its own north and south pole. But if you try to split a piece of empty space in half, you don't get two smaller rooms. You get an absolute void. The distance between those two halves simply ceases to exist. In 2010, a physicist named Mark van Ramsdonk published a paper with a completely dry, academic title, Building Up Space-Time with Quantum Entanglement. He wasn't trying to write a manifesto, but he ended up pulling the plug on the universe's life support system anyway. He wanted to find out what holds the hologram together. If we are a projection, what is the actual glue keeping the image from flickering out? His conclusion is the exact point where this theory stops being a fascinating math puzzle and becomes deeply unsettling. Space is not a thing, it is a byproduct. Imagine two islands separated by a massive deep ocean. The islands don't touch, they have no physical connection through the water. But now imagine that the birds on the first island start singing, and the birds on the second island instantly mimic the song, down to the exact millisecond, without any delay. They are perfectly synchronized through quantum entanglement. Van Ramsdonk's math showed that this invisible synchronization is what actually creates the ocean between them. The distance is manufactured by the connection. Then he did the calculation in reverse. He asked what happens if you slowly turn that connection off. If you begin to untangle the data pixels on the distant boundary of our universe, the three-dimensional space inside doesn't just become empty or dark, it tears. The geometry literally snaps like a dry twig. The distance between your eyes and this screen would instantly pinch shut into a throat of infinite density and then completely evaporate. You wouldn't fall through the floor. The concept of through would lose its meaning because the floorboards and the basement beneath them would no longer have any space to occupy. This is the part that makes my head hurt when I try to process it during a normal day. We look at a vacuum, the empty air in a room, the cold void between stars, and we think we are looking at nothing. We think a vacuum is just a stage waiting for something to happen on it. It isn't. That empty air is a high-maintenance illusion. Every millimeter of space you move your hand through right now is being aggressively held open by a furious, microscopic crosstalk between particles on a boundary billions of light years away. Space is a tense fabric, under constant strain, kept inflated only because the pixels on the outside are whispering to each other. If that conversation hit a single moment of static, the room you are sitting in would fold in on itself like a crushed soda can. I found myself walking through a park after reading Van Ramsdonk's work, looking at the trees, the dirt, the sky, and feeling this sudden, absurd wave of vertigo. I wasn't looking at a landscape. I was looking at a tension headache. Everything was held up by an invisible ledger. But this realization forces us into an even darker corner. If the three-dimensional space we use to measure our lives is just a phantom side effect of a quantum conversation, what happens to history? What happens to the past? Because the moment physicists tried to apply this holographic framework to the concept of time, the entire timeline of our universe began to unravel from the inside out. Time is supposed to be the one thing we can trust. You can look at a photograph from a century ago and feel certain that the moment it captured is anchored safely in the past. But if the universe is flat, the past is not behind us. It is being calculated right now at the outer rim of the cosmos, running in reverse. In 2018, Stephen Hawking and Thomas Hertog published A Smooth Exit from Eternal Inflation. It was Hawking's final academic paper, and it used the holographic principle to dismantle our understanding of the Big Bang. They realized that if you try to trace the history of the universe backward using traditional equations, you hit a point where time loses its direction entirely. It turns into a spatial dimension. The timeline collapses. To fix this, they turned to the boundary. Think of an archaeological dig. We find a dinosaur bone in the dirt and assume the creature lived and died millions of years ago. We think the past created the present, but Hawking and Hertog's holographic model flips the arrow. The bone in the dirt is creating the dinosaur. The state of the universe right now is actively dictating which history is allowed to exist. The boundary doesn't just project your body into the room. It projects your memories and the entire fossil record to match the current data set. It feels like gaslighting on a cosmic scale. Look at a scar on your hand. You remember the accident that caused it. You assume that event is locked into reality. But that scar is just a piece of code on a distant spreadsheet. If the data on the boundary shifts, the history of how you receive that scar shifts with it. Your brain would instantly rewrite its own neural pathways to match the new ledger. You would never know anything changed. This is where the holographic principle stops being a neat physics trick and starts to feel predatory. It robs us of our sequence. If time is an emergent projection from a static two-dimensional surface, then change is a biological hallucination. The universe isn't a movie playing out frame by frame. It is a single, massive, frozen block of ice, and our consciousness is a heat source sliding through it, experiencing the melting as time. But that introduces a massive paradox. If we are just the characters being projected inside this frozen block, how are we doing the experiencing? Who is the one watching the film? To answer that, physicists had to stop looking at the stars and start looking inside the human skull, uncovering a terrifying link between the edge of the universe and the inside of your mind. Your skull is a cage for about 3 pounds of wet tissue. Inside that tissue, you hold your entire world. The color of your first car, the smell of rain, the taste of copper, the exact geometry of your kitchen. We assume this mind is ours, generated locally by electricity leaping across cells. But if the holographic principle is correct, your brain is not an origin point, it is an antenna. In his 2010 book, Decoding Reality, The Universe as Quantum Information, physicist Vlatko Vidril breaks down the cosmos not into matter or energy, but into pure questions and answers. Binary choices, yes or no. He argues that what we call consciousness isn't a magical spark that happens when biology gets complicated enough. It is just the process of information recognizing itself. Now look at the math. The holographic limit of a space the size of your head is roughly 10 to the power of 42 bits of information. That is a monstrous number. It is far more data than your brain actually processes in a lifetime. You are running on an inefficient subroutine. Take an ordinary glass mirror and smash it on the floor. You don't end up with a jigsaw puzzle where each piece holds a fraction of your face. If you pick up a single tiny shard from the pile, you can still see the entire room reflected inside it. It just has less detail. It is fuzzier. Optical holograms work exactly like this. The whole is encoded into every single part. Vidril's work implies that your mind is one of those shards. Your thoughts feel private. They feel isolated inside your head because the pixels on the cosmic boundary are currently arranged to render a localized viewpoint called you. But your consciousness isn't trapped in your skull. It is smeared across the horizon, deeply entangled with the dirt under your feet and the cold void behind Saturn. This changes everything about what it means to be alive. You aren't an observer looking out at a separate universe through two biological windows in your face. You are the universe looking back at itself through a pinhole. The line between the observer and the observed disappears. But if there is no line, if everything is just one massive, interconnected ledger of data written on a flat sheet at the end of time, it means we have completely misunderstood the nature of matter. Objects aren't real. A brick wall isn't solid because it is made of atoms. It is solid because the cosmic code refuses to let two pieces of data occupy the same coordinate. And that realization brings us to a much darker place. If the universe is code, who wrote the program? Or worse, what happens when the code hits a glitch it can't bypass? There is no such thing as a location. We say an object is here or there only because our brains require a coordinate system to keep us from losing our minds. But at the most fundamental layer of reality, coordinates do not exist. In 2014, two physicists named Nima Arkani-Hamed and Yaroslav Trinka published a paper titled The Amplitude-Hedron. They weren't trying to prove the universe was a hologram. They were just trying to solve a practical problem. calculating what happens when subatomic particles collide inside a particle accelerator. Under the old rules of physics, tracking these collisions requires thousands of pages of brutal math, mapping out every possible trajectory through space and time. It is a nightmare of bookkeeping. But they discovered a shortcut that changed everything. If you completely remove space and time from the equations, the math collapses into a single, multi-dimensional geometric object, a joule. When you calculate the volume of this joule, it gives you the exact probability of those particles colliding. Space and time, the very stage we thought we lived on, are just accidental byproducts of this shape. The joule doesn't exist inside the universe. The universe exists because of the joule. Think about a shadow puppet theater. You see a wolf moving across the fabric screen. You see its jaws open, its legs move. You study the physics of the wolf on the screen. But the wolf isn't real. The reality is a pair of human hands moving in front of a lamp in the middle of a dark room. Arkani Hamed's work suggests that our entire three-dimensional universe, including the flat boundary we thought was projecting us, is just the flat shadow cast by a structure that doesn't care about space at all. This is the turning point where the holographic principle reveals its true teeth. We started this journey trying to figure out if our three-dimensional world was a projection from a distant, two-dimensional surface. We treated the boundary like a physical wall at the edge of the night sky. But there is no wall. There is no edge. The boundary was just a conceptual scaffold, a temporary tool to help us unlearn our addiction to depth. The terrifying reality is that the universe isn't a holographic film wrapped around a room. The universe is a calculation that doesn't need a room to happen in. We are not entities living inside a simulation. We are the mathematical equations themselves, thinking they are people. And this leaves us hovering over a sheer drop. If the physical world is an illusion generated by a timeless, spaceless geometric structure, then what happens to the concept of life? What happens to the difference between a living human being and a dead star, if both are just different facets of the same unmoving jewel? The answer to that question blows the doors off our understanding of mortality. When you burn a book, you think you've destroyed the words. You look at the pile of black ash in the gray smoke drifting away, and you assume that specific arrangement of ideas is gone forever. It isn't. Every single atom of carbon, every heat wave, and every photon of light that escaped the flames carries a microscopic record of the ink on those pages. If you had a powerful enough supercomputer, you could track down every particle, reverse the timeline, and read the text perfectly. The universe never forgets. In 2011, a Dutch physicist named Eric Verlinde published a paper that changed everything we thought we knew about why things fall. It was called On the Origin of Gravity and the Laws of Newton. Verlinde didn't just treat the universe as a hologram, he asked what that hologram is actually trying to do. His answer is the most devastating implication of information theory. Gravity is an illusion. We think an apple falls to the ground because the mass of the Earth pulls it down. Verlinde's math proved that the apple falls because the universe is trying to maximize its entropy. It is a data problem. When the apple gets closer to the Earth, the total number of information bits available on the holographic boundary increases. The apple doesn't fall because of a physical tug. It falls because it is statistically overwhelmed by the sheer volume of possibilities on the cosmic screen. Think about a drop of blue food coloring falling into a glass of clear water. The blue doesn't spread out because there is a force pushing the ink apart. It spreads because there are millions of ways for the ink molecules to be mixed up, and only one way for them to stay in a neat little ball. It is pure probability. Verlinde realized our entire lives are governed by this exact same drift. This reframes every tragedy, every birth, and every breath you will ever take. You are not a biological machine fighting against the cold laws of physics. You are a highly specific, temporary knot in the flow of information. You are that drop of ink before it mixes with the water. I sit in my room and look at my hands, and I realize the line between life and death is a ledger error. When a person dies, their body loses no weight at the moment of expiration. The atoms are all still there. The molecules are intact. The only thing that changes is that the highly organized, improbable pattern of data rendering that specific human being begins to dissolve back into the background noise of the cosmos. The information isn't deleted, it just spreads out across the boundary. You cannot be destroyed because you were never a solid thing to begin with. You are an arrangement. You are a song being hummed by the boundary, and when the song ends, the air doesn't stop existing. It just goes quiet. But this realization leaves us with one final, suffocating thought. If our existence is entirely dependent on the boundary's capacity to store our data, what happens when that storage space runs out? Because the universe is expanding, the horizon is changing, and the cosmic hard drive is filling up faster than we ever imagined. Go to the window tonight and look out at the darkest patch of sky you can find. That blackness feels infinite. It feels like a void that goes on forever, an endless corridor of absolute nothing. But it has a hard stop. About 46 billion light years away in every direction sits our cosmic horizon. It is the absolute limit of where light has had time to travel since everything began. And if the math we've been tracking is right, that horizon is the actual surface of the world. It is the solid glass of the television screen. This means everything you have ever loved, every war that was ever fought, every dream you've had in the quiet hours of the morning is currently written out in a frantic, microscopic code on that distant, freezing wall. I find myself wondering what happens when we sleep. When your consciousness dips into that blank state, where does the data go? Is the projection just paused? Does the boundary stop calculating the coordinates of your bedroom while your eyes are closed, only to render them back into existence the moment your eyelids twitch at dawn? We spent centuries looking up at the stars, assuming we were small things trapped inside a massive, three-dimensional house. We thought the goal of science was to map the interior of the rooms. We built telescopes to look deeper into the hallway and microscopes to inspect the fabric of the carpet. We never realized we were just looking at the paint on the wall. The world is flat. Not in the way the conspiracy theorists mean it, but in a way that is infinitely more terrifying. The depth is a kindness. The universe gives us this three-dimensional illusion of space, so we don't have to look at the raw, buzzing numbers of our own existence. It creates a playground where an action can feel like it matters, where a step forward feels like progress, and where a touch feels real. So look down at your hands one last time. Feel the texture of your skin. Look at the lines on your palm. It feels solid. It feels like it belongs to you. But the hand isn't there. The hand is on the horizon, flickering in the dark, waiting for the system to change the code. And you are just the shadow it casts into the empty room.